Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're honored today to have Dieter Fox come and share with us some things that he's been doing across the lake at University of Washington. Dieter Fox is an assistant professor of computer science and engineering at UW. He did his PhD work at the University of Bonn in Germany, and he spent 2 years as a postdoc at CMU, the Robot Learning Lab. And he's been working quite a bit in analyzing the role of uncertainty and probability as a representation for doing tracking and exploration, mapping in robotics. And he also has been working as part of the assisted cognition team at UW with Henry Kautz and others. And we were very fortunate last summer to have Lin Lau, or Lin Liu, one of his grad students here with us as a summer intern, and we heard a little bit about some of the work from Lin this past summer. Now, Dieter will be talking about distributed multi-robot exploration and mapping. Dieter.
Thanks a lot. Thanks a lot for having me over and coming here. Since Lin already gave a talk on some of the activity recognition work we've been doing, today I will focus on one specific robotics project that we did. And most of the work, as usual, has been done by my graduate student here, Jonathan Koh, Benson Limcat Kai, and Benjamin Stewart. And one of the key collaborators on that project was Kurt Conlich from SRI International, because the project is actually based on mostly on a DARPA project. I'll give you some more information on that. And some of the mapping work was done jointly with Dirk Hanel and Dirk Schulz. And Brian Youngstrom was the person who kept the robots up and running during the project. So the name of the project was CentiBOTS, and the idea is to have many robots exploring an environment and then build up a surveillance network. And so that you don't get too disappointed, I will mostly focus on these 4 robots down here. Okay, so the idea is that of the project you have an unknown building, unknown environment, and you want to put in robots into this environment. They are supposed to build a map of the environment, explore the environment, and then build kind of a communication network in the environment and find intruders or track people walking around. And the idea is that first you have, let's say, a wave of more expensive, more capable robots, such as these down here. They build a map of the environment, and later on, once you have a map, you can use the smaller ones, cheaper robots, in order to build up a network and find people in the environment. And our focus at the UW was really building the map of the environment. This is what I will focus on today. Here's just an overview of the complete system. In the upper one, you see the robots. These blue boxes, like coffee machines, are laser rangefinders. So they sweep the environment and they detect obstacles. And by patching this information together, what you can get is something like this here, which is a map of the environment. And the idea is you have, let's say, one control room, and all the robots, they go out autonomously and build a map and send the data back to the control room. And one of the problems is that you cannot assume, if you can't go into the environment before the robots, you can't assume that you have perfect communication. So we had to deal with limited communication, which means robots could get out of communication and things like that. And then you can get these nice kind of 2.5D displays of an environment. And once you have a map, you can send out these smaller ones and start searching for objects of interest. In this specific project, the object of interest was actually, I think, a pink ball, to make it pretty easy on the vision side. But the idea is, these robots, they don't have laser rangefinders. They only have very cheap ultrasound sensors, for example, and a camera. And those sensors are not good enough to really build a map, but they are good enough to navigate in a map that was built by the other robots.
Now, is there any fundamental reason why you'd want to have to decompose the classes of robot, the two different robot types, besides expense?
Yeah, mostly. You don't want to have 100 of these really expensive ones in there.
Yeah. Technically, you could have a laser rangefinder and doing the same task as...
Technically, yes. Yes, if you really don't care about expense and things like that and transportation. So these robots each is, I think, a bit more than 10K. And those are 13, okay, and those are, I don't know, like $200. So it's very cheap. And at the same time, they have also enough onboard processing so that they can navigate to specific locations in an environment. And they can track intruders. And then there was one group at SRI that focused on building up an ad hoc network communication structure between the individual robots. And here on the right, you see some of the navigation capabilities of the smaller robots. So this is Doug Gage, the program manager. You better don't bump into him. So that's why the robot nicely moves around. In this talk, I will give just an overview of the different components that were necessary to do this exploration task. So the first one is robot localization, where we assume you have a map and the robot tries to figure out where it is. This is mostly the task that these smaller robots have to do in order to navigate. The next one is map building. How do you build a map? How do you integrate sensor information over time in order to get a map of an environment? And then I will go to coordinate exploration. What do you do if you have multiple robots that have to do that? And then, given time, hopefully I will go a bit into detail of one specific problem that we had to address in this project. And finally, I'll give you some experimental results. So in robot localization, the task is actually very simple. So this is a graphical model, and you represent the entities that you're interested in by these nodes. These are random variables. And white means that this is not observed, which means we are interested in the robot location in the environment. This is typically the x, y position and orientation of the robot. So it's a three-dimensional random variable. And the subscript t means at time t. And we assume that the robot position at time t mostly depends on the previous robot location, one time step before t, and by the robot control, so which means how the robot moves. And then if we have a map of the environment, then the observation only depends on the current position of the robot. And implicitly, of course, also on the map of the environment. And you can solve this, this problem by a so-called recursive Bayes filter that is given down here. And I'll just show you later some results. There are different implementations of this technique for robot localization. And the key question actually is, how do you represent probability distributions over that state space? And one approach is you just chop it into little pieces. So you discretize your state space. And then you just maintain probability distributions over this discrete distributions, and you get something like an HMM approach, hidden Markov model approach. Other techniques assume that you can represent it by unimodal Gaussian distributions, which are so-called extended Kalman filters, unscented Kalman filters. Then you have particle filters. I'll just show you one example of how that works. And you could have mixtures of these representations where you have multiple Gaussians, and then techniques are called multi-hypothesis tracking, or more recently also Rao Blackwellized particle filters, which is nothing else than the combination of particle filters and Kalman filters. In a particle filter algorithm, how you represent distributions over the state space just by sets of samples you draw from that distribution. And you will see a bit more about what that means. And you update these distributions over these sample sets using a technique that's called sampling, importance sampling with resampling. And what that means is you take this recursive equation where you want to compute p of xt given p of xt minus 1 by first taking a sample set that represents the robot position at time t minus 1. So you take one possible sample that xi t minus 1 is one position where the robot might have been. And then you take the robot motion control and move that sample forward in time. So you kind of guess where the robot might be at the next point in time. And then finally, you give the sample a certain weight, which is called this importance weight, and that is proportional to the likelihood of the observation at that location. And you just do that over and over again, and then you get something that looks like this here for robot localization. What you see here is a map of an environment. Okay, so the gray out here is unexplored. In the middle, you have a lot of free space and some walls. This is actually the old computer science building, Seek Hall. Some of you might have seen that. Not so pretty. And what you see here is global localization of a robot, which means imagine you put the robot in an environment and it has no idea about where it is initially. So you represent that if you take a particle filter by just spreading the samples uniformly all over the state space, which are these little red dots. So each red dot is a possible robot location. And since we don't know where the robot is initially, they are just spread out uniformly. And then as the robot moves around, you update these sample sets using the procedure I just briefly described. And then you get something like this. So the robot is always plotted at the best guess that we have about its current position, which is initially not correct. But you can see, first, these sensor measurements are really, really noisy. So these blue lines indicate measurements taken by a sonar sensor. So you can see that often here we have very long readings, even though the robot in reality is close to a wall. We also developed a technique that changes the number of particles over time. I don't want to go into the details here too much, but you can see that the robot gets more certain because it gets more information, and the number of particles also goes down. This is given here in the lower left corner. So now the robot knows where it is, and it only kind of has to maintain a small cluster of particles.
In your work, do you have any assumptions constraints on the distributions based on notions of linearity or what walls are like and so on? Or is that completely implicit?
So what walls are like, all that is kind of hidden in the sensor model. We don't make any linearity. That's the nice thing about the particle filter, is that you don't have to make any linearity assumptions. In the Kalman filter, you linearize, which means it also works if it's highly nonlinear, but implicitly for it to really work, it should be pretty close to linear. So particle filters don't make these linearity assumptions. And whether you have straight walls or not, that is kind of hidden in the map you give the algorithm. So we don't make any assumptions about straight walls either. Okay?
Can you contrast that with like what the methodology that Hans Moravec typically uses for mapping?
So I'm not yet at the mapping part.
Okay, I'm sorry.
Okay, so this is just give me a map and a cheap small robot with sonar sensors, and I'll figure out where the robot is.
Okay.
Okay, so with this technique, the robot can estimate its location. Hans Moravec, he focused on the mapping aspect, which means how can you get these kind of descriptions of an environment. Yeah, I'll get to that. I'll get to that actually now. Okay, so now we have these robots that can navigate once they know what the world looks like, and the next task is how do you build a map? And just to give you an intuition for why that problem is not so trivial, I'll just show you the raw data we get, and that's now in the Allen Center, when the robot explores the environment. And what you see is, as a robot moves around, it takes these laser scans, and then it can take its own odometry measurements, which means it keeps track of its own wheel encoder evolutions. Okay, and then it can estimate how far it moves, and then you can patch these different laser scans together, and what you get is such a nice kind of, looks already like a map, right? So in the middle you have like white space, the blue line is the trajectory of the robot, and black are the walls that were detected.
No question about the laser scanners. Are they just always facing forward, or are they scanning back?
It's scanning at a certain height. It's just 1D, but it gives you a 2D outline of a patch of the environment.
So about how many degrees?
180 degrees, and it gives you, I think, half-degree resolution, and they're pretty accurate. So lasers.
Every how often? How fast?
10 times a second.
Okay.
More often than you really want to use. So typically you throw quite some of them away. Yeah? So here you can see the problem is that the robot gets more and more uncertain as it moves. And if you just take these raw measurements, so for example, this wall in reality is straight, right, then you can see that it's pretty useless, the map you get. And the problem is now, contrast to the previous approach I talked about, you might say, well, we can do robot localization. But for robot localization, you assume that you already have a map. Okay, so here we have this chicken and egg problem that to localize the robot you need the map, and to build the map you need to know where the robot is. Okay, and I just want to briefly give you an idea. So if you represent that again as a graphical model, then all you do in a sense is you add the map as also an entity that you want to estimate from the sensor data. So theoretically, it's actually very simple. You just put that in your equation, and your equation gets a bit bigger, and that's all. But the problem is, how can you really efficiently estimate that? Because now you need to estimate distributions over the world. A distribution over what the world might look like, yeah?
What's the semantics of M?
M is the map, the world.
What does that mean?
I'll show you what it means. So the map, for example, is this black and white, this occupancy grid. This is, for example, a map of the environment. Yeah? And typically, what most of the people use in the community is so-called SLAM techniques with Kalman filters, where SLAM stands for simultaneous localization and mapping, because you have to do both at the same time. And typically what you do is you represent the environment by a collection of landmarks. And the landmarks could be things like intersections of hallways. A landmark could also be just a line segment that you extract from a laser rangefinder. A landmark could also be like a partial map patch or anything like that. And the world is then just how these landmarks, where they are located relative to each other. Does it kind of answer your question?
Not really, but
So that is the map, a collection of landmarks. Okay?
so M's the same variable at every step in your...
Yes, but you update your estimate of M. So you might add actually landmarks to your map structure over time.
So the graphical model should have a single M variable that's pointing everywhere, as opposed to multiple.
Yes, right. Correct.
Plus, of course, that's assuming stationarity of your map.
Yes, true. Oh, there are many assumptions. Yeah, I agree. So, and in a sense, what you get is just a huge covariance matrix that represents how the spatial relationships between all these landmarks can be represented. And in the robotics community, many people really focus for years and years on how you can efficiently estimate this big matrix, or how can you efficiently get approximate estimates for it. One approach by John Leonard at MIT was kind of to chop your world into local submaps and then try to estimate how these submaps are related, and therefore to avoid this quadratic growth over time. Another technique developed by Udo Frese and Sebastian Thrun, so-called sparse extended information filters, where you use a different representation, a so-called information filter of your map, and you make use of some sparseness of the connections between landmarks. And other technique like Mark Peskin, he got actually the ICHCAI Best Paper Award for developing a technique that is built on junction tree techniques for mapping. Another technique that also we worked on is using raw black-polarized particle filters, which is again a combination of particle filters and Kalman filters. And what we used in that project, actually, also because we were working with Kurt Conlich, is an idea of just keeping track of sparse links between locations. And I'll just give you the idea here. Imagine the robot moves down the hallway and then moves into a room and then into the other room. In a sense, what we do is we take these locations, all the robot locations, and introduce links between them, like probabilistic spatial constraints between them. Okay, and these constraints come from the odometry measurements of the robot. And you can see these little lines. These actually are constraints between different locations. And at the same time, we also introduce constraints based on sensor readings, which means based on laser scans. And then once you have this whole network built up, you linearize it, then you get like Gaussian constraints, and you can globally you can find the globally optimal estimate for the different locations of these scans of where the robot was. So this is how you can solve the mapping and the localization problem at once. I think is this like bundle adjustment? And then you reiterate if you want, because you have to relinearize. Here's another example. The robot actually, it started here, moved around This hallway came up, and then later came back down the hallway. And here you can see that there's some error it introduced. You can see that, for example, here the laser scans don't really line up. And if you are able to detect that the robot came back into this area here, then you can add additional spatial constraints, and you can correct for this error over here. I will show you that on the next slide. It will become a bit clearer. So here's how it works now in the Allen Center. The robot, as it moves, it already corrects consecutive laser scans using a so-called scan matching technique. And as it moves around, it builds up this network of these spatial constraints between consecutive positions. Okay? But the interesting part comes really when the robot closes a loop, which means it gets back to a location where it was previously. And now what we can do is we can add additional constraints here. And then you could see that the robot was able to correct for this error. Here's another example. So whenever the robot closes a loop, then we can add spatial constraints between these different locations. And you can optimize the whole network of constraints. And you can see how the whole map gets shifted around. Yeah?
How does the robot know where to go when it's making a map?
I'll talk about that briefly.
And you'll also talk about how it knows it's back in the same place.
I'll talk about that briefly.
That's critical.
Yeah. So in this case, we actually, what you do is you look at you have some notion of how uncertain you are relative to other locations. And then you can, for example, take your current sensor measurements and see how they match into the other part of the areas with respect to which you might have closed the loop. And then you can come up with some heuristics for the type of the overlap between them in order to make that decision. But I'll talk about that in more detail. Different approach we used. Exploration is actually very, very simple. So all you do is you keep track of those areas where free space is next to unexplored. And all the robot has to do is kind of move to the next unexplored region. It's kind of a standard approach for this exploration.
But in the general case, that's a pretty big search space. You know, many unexplored regions.
In indoor environments, actually not that many.
Oh yeah, I think in narrow chambered indoor environments like
Yes,
this,
I agree. For outdoor,
basically pipes and
Yeah.
set of pipes.
exactly. This technique works really well in indoor, but for outdoor, you want to do something else. I agree. But you can see how when it gets back into these locations, how the whole map gets aligned again. So now we know how to explore an environment with a single robot. If you have 3 robots, once you know the relative locations of these 3 robots, building a map is actually very similar to one robot. So here I think we have one robot over here, one over there, one down here, and one here. And if you think about these spatial constraints, then in a sense you just locally add these constraints, and it's not so much harder whether you build the map with 2 or 3 robots. Okay? But the key assumption for this to work is you need to know where the robots are relative to each other initially. Because if you have no clue where they are relative to each other, then you don't know how to combine their information. Yeah?
On the previous maps, there weren't a lot of rooms on all those hallways. There were a lot of hallways and no rooms. On this map, there's a lot of rooms. Was the search constrained, or were all the doors closed, or no?
I think in the other one, the doors were mostly closed. And we stopped it. So we have some preference for the hallway exploration, and then we kind of stopped it once we had kind of the layout for the right. I'll give you some more experimental results on the mapping later. Okay? So again, the idea is if you know where the robots are relative to each other, then multi-robot mapping is not much harder than single robot mapping. And if you want to coordinate them for the exploration task, that's also very simple. Imagine you have this map and you have 4 robots that share this map. Then what you do is you take these frontiers and you just assign robots to the different frontiers so that the overall kind of travel distance, in a sense, gets minimized. So in a sense, the main task of coordination is just to make sure that the robots explore in different areas. And it's not easy to beat that simple strategy, actually. Yeah.
Was each robot able to make those same assignment decisions, or did they communicate?
In this case, they communicate with each other, and we have. I'll talk about that a bit later. One team leader, let's say. Okay, and the team leader assigns the different robots to the different frontiers.
Did you ever talk about how you Josh's question about landing, knowing you're in the same place?
We'll get there.
Okay.
Yeah. Because that was actually one of the key research questions in this whole project. So where we are right now is we kind of know how to do robot localization, we know how to do mapping exploration with single robots, and we know how to do mapping exploration with multiple robots. But so far, we still make these very strong assumptions that we know where the robots start relative to each other. And in this project, one of the key things we really wanted to solve is the general case of multi-robot exploration, when you can put the robots into any location in the environment initially, and then they explore and come up with one combined map of the environment. So the key problem is if you have no information about their start locations. Yeah?
Are they allowed to recognize each other?
Yeah, sure.
Seems like a pretty powerful constraint.
Yes, I couldn't agree more. We'll see that.
Is that really a common scenario? I mean, I would think if you were going to, somebody's dropping these robots off in some location, are they going to go sort of drop them off and then each one drop them off randomly in a different place? Is that?
You could imagine.
Is this something your sponsors were demanding, or is this?
If you want, you could imagine like the military, right? They have these robots and they just throw them in the windows from different areas in the building or whatever. Then you might have some prior knowledge on roughly where they are, but orientation-wise and all these things, you really don't have a good information of where they are. Yeah?
Seems to me getting them in one window would be a good start.
But one window we know how to do. So I think what we want to do, arbitrary windows. Okay? So why is it not so trivial if you have multiple robots and you don't know where they are relative to each other? This is just like, to give you an idea, so imagine you have these three robots, they start exploring, and you assume they can communicate. Then in a sense, at any point in time, we would like to see which robot, how you can combine their maps, right? And which robot is, what's the relative locations between robot A and robot B. So in a sense, what you can do is you can kind of compare their maps and see how they match into each other. Okay, kind of pairwise. So any wild guesses so far?
How did they know? I noticed 3 different pictures there, but why is one hallway vertical and one's horizontal when there really is no relationship between them at the start?
Oh, because they might be rotated relative to each other. So
do they know do they
no.
have
They have no information about it. They just, initially, every robot starts just exploring on its own. And they all have a reference frame that might say your initial location is 0, 0, 0. And then the key question is, how do you find out, like this robot, where is it now relative to that robot?
So why in these pictures?
Good question.
At a right angle as opposed to just presuming they were.
That's a good point. Would it be nicer to start them all at 0, 0, 0?
Just presuming, that they're all in the same coordinate system.
Yeah.
Are you assuming there are no visual landmarks like office numbers and things like that that you could use?
No unique landmarks, because a priori, if you haven't been in the environment, it's really hard to make sure that there will be unique landmarks and that you recognize the unique landmarks. But we can talk about that a bit more when I get to the solution to the problem. Yeah,
okay.
I agree. So, but intuitively, the key thing is how do we decide whether there's an overlap? And I think humans are actually pretty good. And do we agree that right now nobody would bet a lot of money on any overlap? So now as we let them go on doing their job, then you might say, oh, this is a straight hallway and here's a straight hallway, so that might match. But on the other hand, the size of an overlap doesn't really matter that much, right? Because what counts is the significance of an overlap. Like how unique is it to have a certain overlap? Okay, so in this case, any guesses?
180 degrees
C, yeah. And the decision is mostly made, I guess, based on this area here, right? And there are these kind of 45-degree things. So in a sense, the key idea is to estimate whether there is an overlap between two robots. It mostly depends on what the type of overlap. Okay, whether if it's just a long straight hallway, then we would say, well, a long straight hallway, that's really not significant. But if you have some features that are more significant, then you're much more inclined to say that's an overlap. Okay, and the second problem is, given that there is an overlap, what does it really look like? And that turns out to be much simpler than the other problem. Yeah? So the key thing here is to note is that if you have multiple robots, the number of possible map merges actually grows exponentially, because if you add another robot, for each possible map merge between your existing robots, you might get multiple for the new one, in the worst case at least. Okay, and the other idea is, even if you know the relative locations of robots, you can't just merge their maps by putting them on top of each other. Because in a sense, these maps are not perfect, and one hallway for one robot might be bent slightly in this way, and the same hallway for the other robot might be slightly bent the other way. So you can't just put them on top of each other. You have to somehow integrate them into one consistent map structure. So what we want is a system that is scalable and robust. And on the other hand, we also want to merge maps as soon as possible, because only when they are merged, they can really coordinate nicely. So how can you do the map merging? In a sense, once you have this link structure, this probabilistic link structure for these maps between robots, then what you can do is you can take, let's say, these are the two trajectories of robot number 1 and robot number 2. Once you know at one specific point where they are relative to each other, then you can actually combine their maps into one. And you do that by just kind of adding constraints to their relative poses. Does that make sense? So for example, you could, if you want to combine the maps of robot number 1 and 2, you take the data structure for robot number 2's map, this link structure, and you just take the data from robot 1 and integrate it backwards in time if you want. So that the resulting structure is the same as if it was built by one single robot. Yeah? So it's just kind of like this zippering maps together. And the question is how to merge them just reduces to the problem we need to know one robot's location in the other robot's map, because then we can really have this connection and we can combine them. So on the one hand, we want to really merge them as soon as possible, but we really want to avoid false positive map merges. So we want to avoid that we merge two maps that later on turn out to be a wrong map merge. And the reason why we want to avoid is, so on the one hand side, you could now, of course, say, well, but it would be nice in a Bayesian setting to keep track of all these hypotheses and keep also track of the different possible map merges. The problem is, if you now have 5 or 6 robots, imagine that if the first 2 robots, just by coincidence, perform a wrong map merge, then it could be that half an hour later, you detect that something is inconsistent in your map, but there might be 5 or 6 other map merges in between. So you really want to avoid that complexity that you might really have to go back and undo all your possible map merges and try to find out which one was wrong. So the key idea for the robustness was here to really say, we only want to merge maps when we are really, really sure that this is the correct one. And to do that, well, here we get to the system that the robots, that we have really physical robots, right? So they can detect each other. That goes to your idea, right? So in a sense, what we put on the robots are these markers. This is highly reflective tape. So one robot with this laser rangefinder can detect these specific markers. And then in a sense, imagine if you have a hypothesis for the relative location of 2 robots, then they can really verify whether this is the true hypothesis. Yeah?
How do you detect that the robots are seeing each other? I mean, the lasers, I understand, don't need highly reflective tape, nor will they tell you that there's highly reflective tape.
They will tell me that there's highly reflective tape. It doesn't only tell me there's an obstacle, but you get some reflectance value. Yeah. Okay? So in a sense, now we make the assumption that there are no false positives on that detection process or on this verification process, which actually you can make that pretty safe.
So how do you know which robot it is?
Well, one way to do it is, so the first check is if two robots think they are like a meter apart, then first of all, they first have to detect each other a meter apart. And then what you can do to make it really safe, you can say, okay, the two robots, they actually locally coordinate, and robot A says to the other robot, move a meter backwards. And only if you really see this meter backwards motion. So I'm convinced that you can make that pretty safe. Yeah? So now how do you do this exploration? Imagine you have, again, this partial map, and you have 4 robots. Now there might be a 5th robot for which you have some hypotheses where this robot is in this map. Okay, so assume again, these 4 robots, they know their relative location, and they coordinate. And there's now a 5th robot, oops, yeah, indicated by these green dots. And these, let's say, are 2 hypotheses for where the 5th robot might be in the map. Now, how do you incorporate this verification process in the exploration? You just let the robots not only be assigned to frontiers, but robots can also be assigned to hypotheses of other robots. So in a sense, it might make sense in this context to send this robot to the green one and try to verify whether that is actually the true position of the other one.
All right, so now I'm going to go back to my original question, right? If you have to make if you want your robots to meet up, find they're in the same place, are you really better off putting them in different places to start with, or could you just start them in the same place?
If you can start them in the same place, that's what you should do. I totally agree. But there might be situations when you just can't really do that. For
in the future, if you could search outside, like for instance, what if you had multiple buildings or something?
So if I start them together and they move off in opposite directions. If they all have to meet up eventually, have I really saved anything?
Well, if you have 4 sides of the building and you throw one of these in each window, you're going to cover more distance than if all 4 have to fan out.
Not necessarily, because if there's some redundancy in the search, because so let's say it's an interesting question, right? On the one hand, I get more immediate fan out, but on the other hand, I might have more redundant search. Mm-hmm. And so there's an interesting question of, on average, am I saving search time by starting and then meeting up, or?
I mean, you could imagine now, if we go to this military application, I don't know, but you could imagine that if you throw them all in one location, that one location could be exactly the one where you don't want to have your robots. So you might say I put them in 4 different locations, 3 of which might work out in that.
Well, now you can now adjust what point in time where they meet and how many meet at a time.
To minimize your time. That's a fair answer.
So again, the idea is these robots, they estimate their relative locations, right? And once they have a good hypothesis with this coordination process, then they actually decide to verify a hypothesis. And if they really meet, then that means, well, this was a correct hypothesis, and then you can combine their maps into one. Yeah?
Why not, if the reflective tape is a good landmark for the robots to be able to identify each other, why not have them just drop a landmark, like where they begin? So that way they don't have to traverse back in scenarios where they're exploring places that don't connect to each other. And then if they just happen to go to the same landmark, they can just...
You could imagine, I think, dropping land, but then in the sense you might still have take a similar approach where then the green robot says, yeah, if you want to verify my hypothesis, then these are the landmarks where you should find them. So you could have a similar, take the approach for this context. Okay? And of course, another thing you can do, and this is actually what the other team on the project USC did, is you just wait until they just bump into each other, until they see each other. But that can be arbitrarily inefficient. You could imagine like 2 robots following along the same path, so they might just never meet. Yeah? So the idea here was really to actively verify that. And here's now the result. This is now 3 robots exploring the Allen Center. let's see. Stop that for a moment. What you see is the map as it's being built by the blue robot. Okay. You will also see the green and the red robot at their true location, but this is unknown to the blue one. Okay. So what the blue robot initially does is it just builds a map. It doesn't care about anything what the other robots do. Okay. At the same time, when it can communicate with these two guys, it uses a particle filter to estimate where these two guys might be in its map, to come up with hypotheses for where they are. Okay.
What do you mean when they can communicate? You mean
they could be out of communication range in the real world. That's the idea.
So they're using like wireless or something?
Yeah. There's no infrastructure in the environment, so the problem is really that they might get out of communication range in the middle of this whole process. Yeah? But so what they send to each other is, in a sense, their laser scans, or a subset of them. And then you can estimate where the green one, for example, might be in that map. And you also estimate here the probability whether the other robot is inside the map. So there are two parts of it. Is the green one in the map? This is initialized here with 20% probability. And if so, where inside the map? So there are these two levels. And the particles represent the probability of where inside the map. So now the blue, and the same process goes on the green and the red robot. I'm just showing one. So now the blue robot just keeps on exploring, and green and red too. And now, just coincidentally, the green one actually enters the map. You can see now that the green particles, actually, they all focus under this dot. So given that the green is in the map, the red one, the blue one is actually pretty certain that the green one is here. At the same time, if you look here, the probability that the green one right now is in the map really goes up. And the probability that the red one right now is in the map is very low, just because the sensor data really doesn't match into the map. Yeah.
Was there a team leader in this or some sort of...
So initially we don't have a team leader because they all have the same level, right? And once they merge a map, then one of them is selected as a team leader and it coordinates the others. Yeah? So now what is going on the blue robot again is it's just performing its exploration, but at the same time it also considers going to this hypothesis. Yeah? And only when it's certain enough in this hypothesis, then it's really worth going there and verifying it. Oh, that was not good. Sorry. Let's see that again. There we going. So now I can see these probabilities here now. Goes down. Then over time, the probability for the green one goes up if there's enough overlap. Now the blue one keeps on exploring, and at some point in time, it says it's better to go to this hypothesis rather than keeping on exploring. So it sends a signal to the green robot and says, stop there, or stop wherever you are, moves down, verifies. In this case, it is a true position, so it really detects it. Now, you can see here, it just takes the data from the green robot and integrates it, can you see this, backwards in time. Okay, and the data structure now is exactly the same as if the map was built by only one robot. So now these two guys, they coordinate, one goes here, one goes there. Now just by coincidence, the green and the red robot, they meet. And you can do the same now with the data from the red robot. You take the map and you just kind of integrate it into this link structure, this probabilistic link structure backwards in time. Yeah?
So what happens if the green robot's on the next floor up, right? So the maps are going to be almost perfect now. So the blue guy tells the green guy to stop, and he comes back, and they don't meet. So does the probability of in-map go to 0, and then do you consider the overlap of the maps only getting rid of the previous overlaps, or how does that
So what happens, let's assume in this situation here, right, the green one, or the blue and the green wouldn't have met. So what happens is, first of all the particles that are in that cluster will be deleted, and their probability will be taken off from the inside hypothesis. So in a sense, if you don't meet it, nothing really happens. They just keep on exploring afterwards. They don't merge their maps, because only when they really meet. So in a sense, if they would explore the same 2 levels of the same building, then they would try several times, I guess, to meet each other, but they would never really combine their maps.
But you had a lot of particles there by virtue of the fact that the maps were similar.
Yeah.
Right? So after they get blown away, and now you start exploring some more, and once again, the maps are very similar, right? So do you start accumulating particles?
It would accumulate again, another hypothesis again, and it would try to meet again, and the same process would happen again. Yeah.
But is the similarity between the maps only taken on the new frontier, as it were? I mean, can you say that, okay, I was going around for 20 minutes and they looked really close and I found out they don't match at all, so is that kind of taken out of the equation? Or do you once again say, boy, the last 20 minutes these maps look really close, so I'm going to start accumulating particles?
So what we do with the because we needed to do that in a sequential way, or we want to do it in a sequential way, so it's not really the optimal estimate, but in a sense what you would keep on doing is you first delete those particles, right? And then you would keep on adding over time still particles at the frontiers, because it could be that the other robot always enters the map still, right? And if there's another good overlap between them, then actually you would get a high probability hypothesis again. So maybe we should.
I guess the question is,
yeah.
Can you roll back the data? Is that your question?
But I think it's more like, so these 2 segments matched up really well, but when you realize that you're not meeting them, is there a way to say, well, in fact, this isn't the same segment? They explicitly say, this part of my map is not the same as this part in your map, so that you don't, in the future, match it up again.
It's implicit just in the assignment that we give a very low probability to this relative overlap, to the particles here, because the particles actually represent this possible map merge, right? So if you give them very low probability, that actually means that you say those shouldn't be matched up. There's one situation that goes really into the details where the other guy could kind of exit and enter again your partial map. That is one case we can't really handle well. Okay, but in a sense, by deleting the particles there, we handle the idea. So now you can see here, for example, by treating this whole as one big data structure, the blue robot can actually close loops with the data from the red robot. So there's no distinction between data being collected by different robots.
It was a high-level comment, I guess, which probably would point to a next stage of research. I'm curious if you're getting into this or not. There's a trade between using multiple robots to do configuration and reliability enhancement and to explore more, let's say, on the time pressure, with more of a layout of low-resolution spatial information versus using them to do confirmation and reliability enhancement. And one would imagine that with the utility model and some priors over structures, you could probably come up with a coarse measure value information and actually control that trade. You getting to that at all? You still talk with it?
No, we haven't got. I talked to Tim about that briefly. That what we're actually looking into now is doing some reinforcement learning for this kind of strategy. Okay, to figure out like how to do the coordination a bit better. But we're very much at the beginning of that part.
To do that well, you need to have richer models of likely spaces and usages of the partial map information.
I agree.
So there's still a potential false positive matches here, right?
Okay.
I mean, false positive merges. If you had a highly repetitive environment and 2 of them saw the same sort of landmarks, then would they match? And if they did, do you have a rollback mechanism?
So in a sense, 2 answers. First, they would only match if they would really also meet.
Oh, so you're only matching if they...
Oh yeah, that's a key thing. So we only merge them if they physically meet. That's the idea of that. And in a sense, doing a rollback it's nasty to implement, but you can do it, right? You just keep track of the data, you keep track of the points when you made these decisions, and in a sense, you could implement it so that you could roll back in time. It's just not pretty. Yeah.
One thing that kind of confused me a little bit was when the red robot met the green robot for the first time.
Yeah.
And the green robot had gone down a different corridor that the red hadn't. So, and then when it did the rollback, it kind of corrected the issue. So why did it correct it when there's only one data set that it's...
Because actually, so in a sense what happened is the green map got slightly aligned here, and then the rollback just did a relative correction of that. Okay. What could have happened actually in the rollback, unfortunately it's not in the data, but if the green robot would have already had been in this area, then this rollback could have resulted in a loop closure up here. Yeah? So that's why you have to do this full kind of backwards matching, because you could close kind of loops backwards in time. Yeah?
So when the blue robot meets the red path, do you guys merge it at that point? Where's the maps? Or
at which point?
At the junction where the blue meets the red one, yeah. On the right side. The intersection of the three-way intersection in the middle. Now, that one right there. So when the blue meets that path, do you merge the map at that point, or do they still have to meet up at that place?
No, what happens is they're always in communication, so they communicate all their scans. Okay, so all have the same map structure. And at that point in time, actually a loop closure operation is performed, which means it's optimization of all the scan locations. And that then, the result of that is propagated to the other robots.
I'm just thinking, let's assume like the last path that the blue followed, let's assume that was a ramp going down. You know.
So which one, this here?
The blue line from left to right in the middle.
Yeah.
Yeah. Assume that it was like a ramp that was going down, and then you meet a corridor that looks exactly like the one above. Would it still merge it?
You got me, yeah.
Like that can happen in mining, you know, like
yeah.
mapping mines and stuff.
But then you might want to add more sensors too. And yeah, you can always break.
Well, if you're actually looking at a three-dimensional map merging application, you'd find that the positions weren't matching up because you went down the ramp and your Z value changed.
If it has a sensor,
it's a three-dimensional.
So it's a question of sensors. So. Yeah. And okay, we make the assumption that it's flat.
Is the map correct? Is that hall that the green one explored the curve?
Yes.
Okay.
And talking about map correction, how much do we have discussion already during the talk?
We won't penalize
you. Okay. So just briefly, this estimating relative location. So how do one robot now estimates where the other robot is relative to each other? So again, there are two questions to it. First, it wants to ask, like, is the other robot in my partial map? And if so, where? Okay. So the where is actually pretty easy. So in a sense, you do some sort of localization. But the question is, what's the probability that two maps, you have two partial maps, what's the probability that there is an overlap? Okay. And that gets to the revisiting problem. So, and in general, you can phrase it like, during exploration, is a robot moving through an unexplored or explored region of an environment? And there are two instances to that. And the first one is for single robots. Now imagine this robot is moving around, and we get to this loop closure problem again. Okay, so it's moving, moving, moving. Everything looks nice. And then at some point, it gets back into this area. And the question is, let's see, does it return into this previously mapped hallway, or is it in something parallel to this? Okay, so in a sense, that's a revisiting problem. Does it revisit this same location, or is it in an unexplored area parallel to it? Make sense? So now you can ask the same for multiple robots, which means in a sense, this robot has to ask itself, am I moving through unexplored area, or am I moving through area explored by this robot? So it's actually almost the same as the loop closure robot for single robots, only that your spatial constraints are less. Okay, so that's the problem. And what we need, in a sense, to weight these two, we have two hypotheses. I'm driving through unexplored, or I'm driving through previously explored areas. And what you need is kind of like the likelihood of measurements given that you're explored versus given that you're in unexplored regions of the environment. Okay, and the key problem is where to get these likelihoods from. For explored regions, it's very simple to get the likelihood because you can kind of match your sensor data into the map because you already know this region. But for unexplored regions, it's very hard. Like, what's the likelihood of a certain measurement in unexplored areas of an environment? Okay, and so far, like in mapping, what everybody does is, in a sense, they say something like, if we have an overlap of 3 landmarks, then we assume it's a loop closure. Or often people actually completely ignore this problem and say, we assume it's solved by some other process. Okay, and in a sense, what all these techniques assume is that you have a fixed likelihood of observations in unexplored areas. And of course, in real indoor environments, this is not true, because the likelihood of, for example, seeing a straight hallway patch is much higher than the likelihood of seeing a hallway crossing. Okay, so in a sense, what we wanted to do is come up with a structural model that lets us assess this likelihood in a bit better way. So what we do is, I'll just very briefly run you through, is we assume the world consists of these patches. So it's patched together like a puzzle. Okay, and as a robot is moving through the environment, it just observes a sequence of these patches. So a patch could be a straight hallway piece, or this type of connection, end of a hallway, and things like that. So it observes the sequence of patches, and what we want to come up with is a model that predicts what the next patch will look like given your current patch. Okay, and how you do that is, in a sense, you have a first-order hidden Markov model that generates patches based on your previous one, and you have probability transitions that says QRJ is the probability of observing patch I after you just observe patch J. And in a sense, what we want to estimate for a specific environment is the parameters of such a multinomial, which is the transition probability. Yeah? And again, we'll ignore that mostly. So in a sense, we do that by having Dirichlet hyperparameters over the transition probabilities of this hidden Markov model. And the key thing is that we can learn a prior for these hyperparameters from previous environments. So the assumption is the robot already explored these environments. Each environment has some probability transitions. Like, what's the probability of seeing another hallway patch given that you just saw a hallway patch? And what we learn is the Dirichlet hyperparameter that maximizes all the data you've seen here. And this prior is then used when the robot enters a new environment. Just the intuition. So again, what we do is the structural model is encoded by these transition probabilities between puzzle pieces. Okay? So different environments have different transition probabilities, and we learn a prior over these connections from previously mapped environments. And when the robot goes in a new unknown environment, it just uses this prior in the beginning. Okay? And then when it moves through the environment, it can use the transitions it really observes in this environment to compute a posterior over these transitions. Okay? And then you can use this to predict observations in unexplored areas. And just to show you kind of the effect of this is a partial map. This robot now moves inside the building. Important is this inside versus outside. So you see, since it matches nicely, inside goes up. But now when it reaches the end of the hallway, now you see there was this bump, that the probability of inside suddenly increased much more significantly than before. And that was because based on the structural model, it was detected that a corner overlap is much less likely than such a straight hallway. So this is kind of what this model gives us. And we did some experiments and many evaluations. We can talk about that offline. But we really showed that we get a much higher predictive quality from this approach when compared to alternative approaches such as using a uniform prior or just frequency counting. CentiBOTS. Now again, back to the whole project. So they had, since it was a DARPA project, they had enough resources to have a real test team. So they really wanted to evaluate how good this process is. So we had, I think, they let us in an environment. We were able to test in 1/3 of the environment for 2 days. So our robots were allowed to do some mapping runs. And then on the third day was a real test run, which means they opened up the whole environment, and we just had to let the robots go out and build a map and then come back. The key thing here was really that even we were not allowed to look into the other areas, so we had no idea what it looks out there. I think this is the most rigorous evaluation of a mapping technique so far, because typically what you do is you have your own lab and you do some mapping runs, and if it doesn't work, you tune some parameters and do it again, and then you publish your paper. But here we really had to make it work even without knowing what the environment looks like.
What was performance criteria?
Performance criteria, oh yeah, we'll get to that. Time and quality, in a sense. And it was pretty frightening, especially the first run. We did that with a single. So this is kind of the command room. And so the robots communicated wirelessly. In the very first run, we did one robot. And in a sense, so here, and they set up in every room an overhead camera so that they were able to see how the robot explored. But we were not allowed to even see that. So during the run, we were really sitting there and had no idea what's going on, because after some time, so the robot here, you can see it starts exploring, building the map. This is now in the control room. And then at some point, it lost communication. So I think for 10 or 12 minutes, we heard nothing from this robot. We didn't get any data, anything. So it really felt like this Mars exploration, right? Out of communication, you just wait for the signals coming back. And then after a while, really suddenly in the map, all these different patches, it came back in communication. And not my video, sorry. And then suddenly all these patches came up. And you can imagine that some people were pretty happy about that. And then once that was done, you sent in the other robots, and they had to really kind of build up this communication network then. But you can see, again, here's a robot exploring, just because we're running out of time. Now, talking about evaluation, so here we did the mapping only with 1, 2, or 3 robots. The mapping time actually goes down if you add more robots, which is actually nice. There was another team that also did this, and I think they typically took 50 minutes for the mapping. So we were pretty successful here. And mapped area, so how do you evaluate the quality of a mapping algorithm? There are 2 things what you typically do. First, you do simulation, because then you know the ground truth. But the problem is simulation is just a simulation, so you don't really know how realistic your simulation is. The other approach is typically you just show some animations and show people and say, like, this looks correct, right? So what they did here is they had a person spending 3 days tape measuring the environment. Okay, so to come up with a ground truth map. And then...
Were those the 2 and 3, did those robots start in random locations? Or?
One of the 2 started in random, the 3 started from the same. Random location is actually not as fast as from the same. Interesting, I know. So what you see here in this brownish tan color, this is the ground truth they came up with. So again, they spent days on measuring it. And overlay is kind of, this is our map, and you see there are some discrepancies between them. But the nice thing is that the evaluation team actually agreed that our maps are better than the ground truth maps they generated. And one indication for that is, for example, these are 3 maps that were built in completely different runs. So one was built with 3 robots, one was built with 2 from different start locations, and one was built with 1 robot, completely autonomously. And you can see that they are virtually identical. So that shows you that, for example, if they estimate these tables to be over here, all 3 of them, then that is more accurate than what the people measured with their tape. So this is one of the outcomes really saying that we are better than what you can do with a measuring tape. Of course, you don't want to do it with a measuring tape in the first place. Okay? But that was with mapping evaluation. So the key thing here was really this distributed multi-robot exploration from unknown start locations. And we developed this particle filter to do this partial map merging and partial map estimation. And this active verification, I think, is really something that helps you to keep also to increase the robustness and to keep the complexity of the reasoning lower, so that you don't have to reason about all these possible hypotheses. And the Bayesian model, that I'll just skip that, but in a sense, it really also, I think we showed with that it really helps robots to build strong prior models of environments and to use those. And we really want to get further in that direction because I think so far people really haven't done that. So the robots use the same reasoning no matter in which environment they are. And we really have a technique that adapts over time to that. And some other works is building object maps that detect like walls and doors, search and rescue. If you have an outline of an environment, we want to do reinforcement learning for these better exploration strategies. In outdoor robotics, where we want to do some more on this lighting condition estimation. And we also do some location estimation, activity recognition. And yeah, maybe I'll talk about that next time. Thanks a lot. And great. Sorry. Yeah.
On the hierarchical Bayesian model that you had before, what were the hyperparameters and how many did you have again?
So we had, I don't have the number, but let's assume if you have 20 different types of patches. So we assume you have a discrete number of patches.
Okay.
Then you need, for each patch I, the probability of the next patch.
Right.
So it's a multinomial with 10 bins, and we have a Dirichlet prior on this multinomial. And we learned that from this previous environment. And we also showed that using this technique really helps you. I mean, one alternative is to just say you start with a uniform prior, but of course that gives you really bad performance, right? And the other technique is if you want to learn that prior from previous environments, you could just take all the data you know from other environments and do kind of frequency counting on them to get that. But that also turns out it doesn't give you a good prior because it's way too strong. And then there's this question of how strong your prior should be. And this hierarchical technique also estimates the strength at the same time. So the shape of the Dirichlet and the strength. Okay? We can, I think you were first.
Doesn't the probability of the next patch depend on which direction you're going? I'd assume that if you have a straight hallway and a T, it would be probably shorter.
I agree. So in a sense, this was mostly to show that you can do that and that it works. So the model we have is very simple because actually you don't have this just kind of one-dimensional string of things. But we assume that on average, actually if the robot follows a certain exploration strategy, that it gives you something already much better than not using it. But I agree, you can do much better. We also think about using better kind of spatial models that really take into account like the observation at that time. I agree.
Have you, so, sorry. But I was thinking as a human wandering around an environment, I'm used to the fact that corporate architecture is fraught with symmetry. And after a while, I begin to rely on that. And I'm wondering if you can envision a system down the road that, you send out a few robots, and then pretty soon the robot system knows or leads to this conclusion that there's a symmetric part of the building. There's a couple of extraordinary examples of that on campus here. It would be great fun to unleash your robots.
I actually think that this is, so this hierarchical reasoning we do here, this is pretty the beginning, let's say. But I think, so one of the reasons right now why most of the mapping techniques don't use strong assumptions. So for example, it's a reasonable assumption in most environments to say you have straight hallways and they are perpendicular. In most environments. So the thing is, if you do that, then people are going to tell you, well, but it's not going to work in my environment because we have these other structures, right? So the only solution people have to that problem right now is to say, I don't even make that assumption. I think it's much better to have a robot that has higher level reasoning and says, am I in an environment where I can make that assumption, and condition on that reasoning, I can really make much better sensor interpretation, right? And if you send it in a different environment, then it should just not make this assumption anymore. So this is where this whole hierarchical reasoning goes in, and I think there's great opportunity for improvement, yeah.
A baby step may actually be to just say, oh, this looks like the second floor or the third floor of a building, of the floor. I've already learned one of the floors.
Oh, yeah, if you want to transfer that, yeah.
Whereas they may not be exactly the same. There may be some modifications to the building, but it's enough to get around.
I agree. So we also want to go taking into account the outline of the building, because you might have something from an aerial image, where you enter, then you can make reasoning to my right there's only one there can only be one room, for example, or things like that. And then you should be able to improve your strategy. Yeah.
So, obviously this is a lot more interesting, but I mean, why couldn't you use something like GPS or measure distance between the different robots using like a radio transponder or something like that?
The GPS doesn't work indoors. Should I say fortunately? I don't know, but otherwise everything already.
Well, okay, why not radio transponders then between the robots measuring the relative distance?
You could do something more behavior-based where you say you take into account like the signal strength and then compute maybe a gradient in signal strength.
Or the time or the frequency shift or something.
When you have a line of sight view of the other robot?
You don't need one.
But if you have rooms between them, then it's really tricky. The communication gets very, very bad. So we had major problems here with communication, even though they're part of the team focused on nothing else. So for example, we assume we can make the assumption that A can talk to B, then B can talk to A, which is not true. Or if A talks to B and B to C, like the transitivity, all these things don't really work.
Yeah.
So it was already a major step that the system was able to deal with limited communication. Typically, all the systems out there assume that you have like full communication all the time. Yeah.
How robust is it to people walking in the environment, people opening doors, someone picking up the robot and turning it around? Don't pick up the robot.
Don't pick up the robot. The mapping, people walking around is kind of okay. A person, because we make the static world assumption, so a person really standing in a doorway is not really pretty right now. So the robot would, I guess, decide it can't just explore there. But that's also where this other research goes to object maps. So where we want to come up with map building techniques that reason about what are walls, what are doors, because as soon as you reason about doors, you can say, I expect this thing to move. Or I'm not surprised if it moves. But if a wall moves, then you're much more surprised. And then with this kind of reasoning, you could also then incorporate people and things like that. So that's actually the next step. I think if you just want to build a map and explore, then we're kind of pretty close to saying that works now. That works well enough so that we can say most of the research is done. But I think on getting to these object level maps, like a much more symbolic representation, there's still a lot of work to be done. Because the reasoning is much more complicated, actually. Yeah.
So in your that test phase, you said you got to go in for a day and play with a third of the building. What did you tune in that day?
We didn't tune that much. So the thing is, we had for this whole project, I think we had a bit more than 12 months. So when you get there, not all the code is working yet. So you still tune some parameters for the exploration, for example. You don't only go to the closest frontier, but you also want to evaluate which is a good frontier, which is a bad frontier, things like that. But we didn't really tune anything. And especially because we didn't know what these other areas look like.
So there's nothing about the area that would clue you in into different things to do?
No, we didn't do that. It would be, it would be nice, right? That's actually what you want, that the robot says, well, I expect the other parts to look similar, so yeah. And that's where really a lot of room for further research. Yes.
One last question.
No.
No. Thanks very much.
Thank you.